Welcome to Mr. Math Academy. Grow your math brain.
Hello friends, welcome back to Mr. Math Academy. So here in this video we solve the numerical which is rectangular plate he has given. Okay, so this length is this width is 35, this thickness is 35, and the length of the member is it's a 500 mm is given. Next thing is what happens if you just apply axial pull of this member, that is the material, the length of this member will be increased to a 0.2 mm. Okay, in the same case, what happens if he has applied a load of 122.5 kilonewton, 122.5 kilonewton on this right angles here, that is with respect to this in this case. So in this direction he was applying a load, that is a tangential load is applied. So in that case what happens, the member will be, the distortion can be takes place, that is the corners are deflects into a 0.00125 radians. Means what she has given exactly here is, so one thing is he has given the axial load is given, with respect to that there will be a change in length is given, and again in the other case if he has applied a tangential load of 122.5 kilonewton, there will be a deflection like a shear strain will be takes place, which is of a 0.00125 radius. So now this will be the given data here. So now what we have to find out here is, we have to find out what will be all the four elastic constraints here, like Young's modulus, bulk modulus, modulus of rigidity, and we have to find out one more term is it's a Poisson's ratio. Now we'll just solve how to simplify this, it's how we can solve this. The problem is very simple, only thing is we have to remember that what will be the relation between the elastic constraints here. Okay, we'll just solve here, directly we'll go for the solution. Okay, before that I'll write the data here. So he has given the axial pull is 100 kilonewton is given. So again he has given, okay, there will be a change in length is equal to 0.2 mm is given in the x direction, or you can take it in the axial direction. So again he has given the capital V. Capital V, what I have taken here, it's a like shear load, that is a tangential load I'll take, so which is of 122.5 kilonewton, and again because of this shear load, okay, there will be a strain is created which is of 0.00125 radians. So these are the four terms. Along with that he has given the dimensions of the member here. So this you can take the dimensions over here. So this is a cross section, so he has given this is 35, so this is also 35 is given, that is a thickness and the width. So this is your 100 kilonewton, that is the axial load. So because of this axial there will be this is the actual length of the member 500 mm. Because of this 100 kilonewton the length is increased to the some 0.2 mm extra, that will be the change in length in the x direction. Now we'll solve how we can calculate the other terms, like four terms. So we have to find out, so we need to find out Young's modulus E, bulk modulus K, modulus of rigidity G, and the Poisson's ratio. These four terms we have to find out. So I'll find out one by one in a proper way. We'll go for the step by step. So first I'll go for the Young's modulus E, how we can solve. So I'll take Young's modulus E is equal to, it's a ratio of normal stress to the normal strain, normal stress to the normal strain. I'll take like this. Now again, what is the normal stress is nothing but what, it's a load which is acting in a direction, and again we have to take this area, we have to take in which the load is acting in the perpendicular direction, we have to take. So the normal stress become, it's a load by area. I'll take, this is F by A. The strain is nothing but change in length to the original length. This is our strain. Okay, now we just simplify this. Force means it's a 100 into 10 power 3, that is the axial load. A means that is the area of a cross section, we have to take this area, I'll take, that is a 35 into 35. So this numerator complete, it will give the normal stress here. So again the change in length is 0.2 mm. So in the denominator part it's a actual length of the member, that is a 500 mm. So finally it gives the value of a Young's modulus, that is around, I'll take here, I'll get the value is around 204.08 into 10 power 3 megapascal, or I can take in terms of gigapascal, that is 204 into 08 gigapascal. So this is the Young's modulus of a given material. Okay, the next thing we'll go for the other terms. We'll find out the modulus of rigidity, because some data he has given for the modulus of rigidity. So we'll consider the modulus of rigidity. G is equal to, it's a ratio of shear stress by shear strain, that is a tau by phi. So directly he has given the phi, that is a 0.00125 radius. Okay, only thing is what we have to find out, what will be the shear stress. So shear stress means the tangential load by the surface area we have to take. So again, so this tau is nothing but, so here in this case we should not take the 100 kilonewton, because since it is axial load, so we have to take 122.5 kilonewton, because he has changed the direction of the applied load, because he was applying a load in this direction, on that particular direction. Okay, I'll take, so because tau is equal to V by area, so divided by phi. So V means it's a tangential load, it's a 122.5 into 10 power 3. So area we have to take only this area, because the load is acting, now he has changed the position, but the area is remain same. So I'll take 35 into 35. Okay, divided by phi is nothing but it's a shear strain, 0.00125 radians. Now finally if we just simplify this, I am getting the value is around 80 into 10 power 3. 80 into 10 power 3, it's a megapascal, or we can take this as 80 gigapascal. Now these are the two parameters. Now let us move on to the other two terms, like bulk modulus K and the Poisson's ratio. So to find this, so we will be having somewhat the relation is there. So we just remember that to find out the other terms. So we will find out the Poisson's ratio nu. So we know that E is equal to 2g into 1 plus nu. That is the relation between the Young's modulus E and the modulus of rigidity G here. So E is we have calculated, G is also we have calculated. Just substitute the values, directly we can get the nu here. That is easy in the nu. That is a 204.08. This is 2 into 80, 1 plus nu. I'll just remove this. Now if you just simplify, it's a simple thing, the simplification is, so finally I'm going to get, it's a Poisson's ratio, it's 0.2755. Now this is the Poisson's ratio of the material. So finally we know that the relation between the other concept, that is the Young's modulus and the modulus of bulk modulus here. Suppose if I take, there is a last one, we know that E is equal to 3k into 1 minus 2 nu. So this is the relation between the Young's modulus E and the bulk modulus K. So E is nothing but it's a 204.08. I'll take in terms of gigapascal only, so that at the end I'll get the K value in terms of gigapascal. So this is 3k, 1 minus 2, this is 0.2755. Now if I just simplify again, okay, first I'll simplify this part, again we subtract with the minus 1, okay, again if I cross multiply with respect to this 204.08, and again if I just divide this by 3, so finally I get the K value, that is the bulk modulus is, it's around 151.5 GPa, that is a gigapascal. This is the bulk modulus here. So these are the four elastic constants here, that is the Young's modulus E is equal to 204.08 gigapascal, the modulus of rigidity G is equal to, it's around 80 GPa, 80 gigapascal, and the bulk modulus K is equal to 151.5 gigapascal. Finally the Poisson's ratio is equal to 0.2755, we are getting the value. Okay, this is a very simple problem. So if you just remember what is the relation between the elastic constants, so easily you can solve any kind of problem. Okay, if you just like this video, please comment, share it to your friends, and subscribe to our channel. Thank you.